Good, but let's continue with Mass-univariate fMRI now. So now what we want to discuss after introducing the GLM now in this form and in an abstract manner. So we've now established this and this.
There is no
So we now established the GLM in this form, and we've seen one example for a design matrix. So which example was that? Not the form, but which method did we discuss for the design matrix? Last week, when we plotted this, we discussed one statistical technique. I think I see it there. No, we discussed one statistical modeling technique as a special case of the GLM last week. That you know from undergraduates, from your undergraduate studies. In terms of the design matrix, because the design matrix now encodes different forms of statistical designs or statistical techniques or statistical methods. And we've looked at one technique in particular. I also see it there. How was that called? What you have on the left side there?
No. Discrete time systems.
Jesus, what is going on with you? When we did this here, what was that called? Exactly, so we discussed simple linear regression. Yeah, but so all of this is, so these are not just terms that I make up and so on. So these are, if people talk about simple linear regression, this is what they mean, right?
First week we were mainly talking about multiple linear regression.
Yeah, we also talked about multiple linear regression. Actually, we will talk about multiple linear regression more now. But one thing that we discussed was simple linear regression. And always remember that simple linear regression corresponds to a design matrix of this form. Just memorize that. And so this is the first example that we've seen for an application. And we also did a little bit on multiple linear regression. And now we want to actually discuss more on multiple linear regression for the analysis of fMRI data. Because this is essentially a multiple linear regression technique, at least at the first level when we analyze the observed fMRI data. Good, so now first think back in terms of neurocognitive methods. What is the, once you have acquired fMRI data, what's the data format? So how are the data, what are the data and how are they organized?
Matrices.
Yeah, and what are the rows and columns of these MRI data matrices?
Rows and columns.
Yeah, what are they?
I couldn't understand the question.
So if you have a data matrix, that means you have something like, let's just put in some, come up with some values here. And I will just write out a data matrix and then you will need to give me some meaning for this. Yeah, wait a second. Let me finish. Well, that takes a little bit of time. And 83, 1. So now we have a data matrix, and we here have some columns, and we here have some rows. So it doesn't matter which order, but what are the columns indexing, and what are the rows indexing?
X and Y axis.
Don't guess. Either you know it or you don't. Or well, guess. Have a guess. So So think about fMRI data, how that is organized, and now think about fMRI data in a data matrix. So what can the columns and the rows mean? Yeah, exactly. And of course, this is either or. So of course, you can organize it like the voxels being the rows and the time being the columns, or the other way around. We will actually, and this is in some way important, always use the format where the rows refer to time points. So these are time points. And the columns refer to voxels, so locations. Let's do voxel 1 here. And then we have voxel NB, I call it. So that's just number of voxels. And time points, so images or TRs, we have NT. So this would be, yeah, and what are these numbers again? Do you remember what these numbers refer to? Exactly, that's just the gray level that is in these pictures. If you plot one time point and you plotted this row in the right spatial arrangement, then you of course see the picture of a brain. So these values are just MR signals or gray levels of your images. That's the best way to think about it, because what you are doing in fMRI data analysis is image processing. You have a sequence of images, a time series of images, and you want to analyze that. So basically you have a spatial temporal data set where you have space corresponding to voxels and time corresponding to the images or the time points or TRs. And now the first thing to realize about fMRI data analysis is that when using a GLM analysis, one focuses at the computational level and at the modeling level at one voxel at a time. Yeah? So focus on one voxel. And this is correct as far as modeling the data is concerned. So we will set up a design matrix that is meant to explain the data of one voxel, and this design matrix will be the same for all voxels. Yeah? So essentially there's one design matrix for all voxels, and it's also true in terms of how the design and the model for fMRI is usually visualized. Once you do look at the p-values and you compare the statistics that you observe to the null distributions of these random fields, then actually it becomes clear that the statistical model that is about this is actually not a univariate model, but a infinitely or uncountable multivariate model. But for the moment we leave that out, because this we will do at the end of the winter term, where I show you then the entire probabilistic model that is behind doing statistical inference on fMRI data. For the moment, we focus on a single voxel and the standard notion of calling this Mass-univariate, because it's univariate because we focus on the data of one voxel, and it's mass because we have many voxels. Yeah? We will later see in the end that actually when doing statistical inference, this has always been a multivariate model, but this is not the typical story actually, but we will see that, and that's the case. So also when you hear people talking about multivariate methods like SVMs or classification and so on, and comparing this to the Mass-univariate GLM and saying that the GLM is a univariate method, it's true in terms of the computations that are being done, in terms of the estimating the parameters, and in terms of the model being identical for all voxels. But in fact, if you do statistical inference based on random field theory, then your model is actually not a univariate model, but a highly multivariate model. But we will get to that. We will come back to that. For the moment, we follow the traditional way of looking at this as a Mass-univariate approach. And then in terms of the GLM, we now want to develop a multiple linear regression for that. And of course, we now we can write this as our standard multiple linear regression, where we take our yi and model this by a number of independent variables up to p, and of course have our epsilons there. Now, what is this referring to? So this is the MR signal at time point I, where I goes from 1 to the number of time points, and the number of time points usually refer to either one run, or let's say if the participant was scanned for 3 runs, and during each run there were like 300 images taken, then that would be 900 time points together. And this yi is the MR signal at a time point I for one voxel. And because it's for one voxel, and we basically separate the data over voxels, I don't index the voxel here. So in principle, you could also have like a little v here that says this is the MR signal of voxel v at time point I. So then it would be, for example, this would be voxel, this would be y11, and this would be y 2, 3, but because this is always the same for all voxels, we just index time and not the voxel.
Sorry, I couldn't catch the point you have made. For each voxel, each participant has 3 what? 3, we said something like this, but...
Now, for each voxel, each participant has as many time points as there are volumes or brain images acquired. So, for example, if like 300 images were made during one run, then there would, for each voxel, be 300 time point R signal values, and if there are 3 runs, for example, then that would be 3 times 300, so 900 time points. Right? So always when studying this, link this back to neurocognitive methods and how data is organized. Yeah, everything is important that I said. Nothing is just because I want to talk about emotions or something. Everything is important, and nothing should be forgotten. So this is now one time point for one voxel. The xi are, of course, the regressor or independent variable value for time point I, again from 1 to nt, and how these regressors are formed. This will be the big topic for next week, but I will show you roughly how they are formed today. The betas are, of course, the parameters and their intuition. Yeah, we will also have a look at in a second. And then there is, of course, also the ith error contribution. So essentially, the only thing that I've said so far is that that is now different from what we've seen so far, is that the yi is the MR signal of a single voxel at a given time point. And of course, we can then immediately write this in terms of the GLM form, structural form, where y is now nt. I think we will mainly leave it with n, but just to make clear that y is a time series. Yeah? Hence also of one voxel. Hence it's a vector and has as many entries as there are MR signals for this voxel. This is also why I arranged the data like this, so that space is in the column dimension and time is in the row dimension, so that these the entries here are already, or the columns of this matrix are already the vectors that are then modeled. Yeah, so this is important. So this you should immediately memorize, so that the y, if we talk about fMRI data, is the time series of one voxel. That might have like 300 entries if there are 300 images taken, or 900 if there are 900 images taken. Good. So the question is now, what if this is our data in fMRI? How are the design matrices formed, and what do the parameters, what do the beta parameters mean? The error is again a Gaussian error term that will then later allow for maximum likelihood estimation and so on. And to make this transparent, I have set up this little example that we can now look at. So maybe we leave it like this and just zoom there. So this is now an example which I'm trying to make a bit bigger. So now think again about an fMRI paradigm, yeah? And there's a participant who's in the scanner, and you present two kinds of stimuli to the participant. So what were the stimuli there? Arousal and valence. So then you so this would be a stimulus that is high on valence, and the other one is high on arousal, let's say. Yeah. So this is a high valence stimulus. If this is possible, I actually don't know.
Just other, I think in this case it would be high and low valence stimuli.
Okay, then. Okay. Yeah, that makes, I guess, a little bit more sense. So what would be a high valence stimulus, for example?
It presents an effective picture.
Yeah, but what is a high valence?
A cute dog.
A
cute dog.
And what is a low valence stimulus?
It's more negative.
Okay, so this would be a cute pet. No, it's important because this is exactly how these kind of studies work. And so this would be, so it's not high and low, but positive and negative, right? So this would be positive valence, and this would be negative valence. Of course, this is also high and low, but they call it this negative valence stimuli, and this would be what? No. Good. And now, so the participant is in the scanner, and there are these cube PET stimuli, which are positive valence, these injury images, which are negative valence. And now, at a given point in time, and here at the x-axis you see time, at a given point in time, only one image is presented. And you see here that at time I don't know, 15 or something, and actually at time 0 also, that's a little bit hard to see, but at time 0 there's a positive valence stimulus presented, and then at time 40, so around here, there's a negative valence stimulus presented, so cute cat, cute dog, and then injury of a knee, I don't know, then cute bird, and then injury of a hand, and so on. Yeah. So this is how things are being presented. Now, in fMRI data analysis, the aim is now to create a generative model of the observed MR signal. And to do that, of course, the idea is not that the MR signal does such a spike, but that at the time when such a spike or when the image is shown, the MR signal does what it always does, namely to go through the hemodynamic response function. Yeah? So the idea is, if you present a stimulus here, so here at 0 the stimulus comes about, then this induces activity, for example in visual cortex, both activity that rises to a peak roughly 4 seconds after the stimulus and then returns to baseline around 12 seconds after a stimulus onset, then maybe does this post-stimulus undershoot and then returns to baseline after 32 seconds. Yeah? So this is, whenever you show a stimulus, the assumption is that such a hemodynamic response function is evoked in the brain. So if one looks at this now in terms of the predicted MR signal, this is what would be seen. So so now we need actually both. So focus on this side here. So here we have the blue stimuli, and whenever there's the stimulus shown, and in the onset function you have such a peak or event, it's also called, then the prediction about the MR signal is that you observe a hemodynamic response. And what you see here are just these functions, but a little bit squashed together in time. So you see that instead of a peak, you have kind of this behavior of a hemodynamic response function. Yeah? And basically going from these stimulus onset functions, which just encode at what time the stimulus was presented, to the predicted MR signal, this process is known as convolution. So this going from here to there is a stimulus onset convolution and convolution with the hemodynamic response function. Yeah, so for the moment if you just look at it, what happens, of course, whenever you have a peak here or a spike here, you get a hemodynamic response function here. So you can basically also view it as just plugging in a hemodynamic response function whenever there was a peak here. The same for the other stimulus. So for the negative valence, whenever there was a stimulus presented, in the prediction of the MR signal, you have a hemodynamic response function at this location. This is not quite how convolution works. It's not that you have kind of a data or a vector here of values and then you just replace certain values with other values. We will talk about what convolution means and how this entails the notion of linear time invariant systems next time. But for today, it's essential that you appreciate that from a stimulus onset function, you can generate a predicted MR signal function. Yeah, so you predict that the MR signal evolves like this. Of course, only if the voxel that you're interested in is actually sensitive to positive or negative valence. Yeah, so that's how the prediction is formed. This is all model formulation, yeah. So this has nothing to do with data. But now we look at some data, and maybe have a look at the voxel A and voxel B. So you see voxel A. This is now of course simulated, but MR data, and you see that voxel A goes up and down and then stays a little bit down and then goes up and down again and then goes up and so on. And voxel B shows this kind of behavior. So in terms of the condition of high and low valence, what was this again? Positive valence, right? So this is positive valence. And this is negative valence. Wow, interesting. What can you say about voxel A and voxel B? Is voxel A sensitive to positive valence, to negative valence, to neither, to both?
To positive valence.
Yeah. Why do you say that?
Because the pattern is so it's a time. There's a signal change in the MR signal when it's supposed to be, so every time we have onset of acute pattern.
Yeah. And what about voxel B?
Both. It's active to both.
Yeah. Exactly. So this, maybe just say again why you say that.
Because every time when we show any picture, there is a response in our signal, so changes.
So let's say that this is some brain region here. Would you call this brain region of voxel B? Is this a brain region that's coding positive or negative valence, or neither or both?
I think that it responds to, it doesn't code valence at all, but probably it's something very early.
Well, I mean, it could code valence, but responds equally strong to positive and negative valence. Yeah. It can also be that it has nothing to do with valence and just responds whenever there's a visual stimulus. Yeah. What about voxel A? Does this encode for positive or negative valence, or both, or neither? So definitely it doesn't represent negative valence. So whenever there's a negative valence stimulus, it doesn't respond. So it has something to do with positive valence. Of course, if your positive valence are animals and your negative valences are injuries, then you cannot really say that this is valence, but it could also be just being responsive to animals versus injuries. Yeah, but that's kind of the logic
the
here.
prediction of MR signals, this convolution process, the same thing with the encoding stuff. I'm always confused about this term sometimes when I try to read something.
Yeah, I mean, we will discuss decoding in the summer term. Convolution is just the process of convolving one function with another function, which we will discuss next week in detail, and then we will see what convolution is. Sometimes people use decoding, use a GLM when they generate, for example, beta parameters, which they then want to decode and so on. So it's not the same thing. Convolution is one thing, decoding is another thing.
I also just learned that general linear model and generalized linear model are different things.
Of course.
I just thought they were same.
No, everything has meaning. You just need to look very closely, and these are all different things.
Had the same name, I think. The owner of models should change it before. I think it creates.
No, this is about, yeah, but the thing is, learning about science and being a scientist is about learning the language, right? And then it's important to be precise about the terms and know what they mean, and don't assume that everything is simple. Everything is quite complex. So now this was kind of the interpretation when we look at pictures. Now we look at the same thing from the design matrix perspective and the better perspective. So now what we've seen here were predicted time series. Yeah, so we've seen this. In the GLM, these predicted time series correspond to regressors or independent variables. Hence, they form the columns of the design matrix. Yeah? So again, now think about this was positive valence, and think about the time series that we've just saw now encoded in terms of the gray levels of this column. Yeah, so you remember there was a stimulus fairly early on, then there was another stimulus fairly early on, and the negative stimulus was only the third stimulus. Yeah, so these columns of the design matrix are these time series that we see, the predicted time series that we see here. Yeah, they are just represented in a different way. So basically, you can also think like you view these two from above, if you want. But the important thing is to appreciate that these are the predicted time series. Yeah? So this is the predicted time series of positive valence, and this is the predicted time series of negative valence. And these predicted time series, of course, they have many different names. They are also called predictors, like I called them here. They are called regressors. They are called columns of the design matrix. They are called time series of the independent variable. It's all the same thing. Yeah? Columns of the design matrix, that's the important thing. Regressors or predictors. And now what we've also established is that voxel A is only responsive to the positive valence. And now the crucial thing is that you appreciate how such a responsiveness is expressed in terms of beta parameters. Because if you look again, what happens here is that whenever there's a peak in the positive valence, there's a peak in voxel A. Whenever there's a peak in negative valence, there's no peak in voxel A. And this is encoded in beta parameters by having a large value, or let's say 1, for the first predictor and 0 for the second predictor. Because if you form the matrix product, you will always multiply the first column with this 1 and add to it the 0 multiplied by the second column. Yeah? So you need to appreciate the matrix product. And then what you get, if you also add some error, is some observed data that, as you can see here, if you compare what is in YA and the predictor 1, you see that the bright bars, so where the signal is large, correspond to one another. Now the other thing is that if you have the voxel B, which responds equally well to both predictors, this can be encoded in terms of the beta parameters by assigning this essentially the same weight to both beta parameters. Yeah? So in terms of the design, the matrix multiplication, if you do x times beta b, you multiply what you have in this column by 1 and add to it 1 times what you have in this column, so for this predictor. And then if you are here, you get this thing. If you're here, you get this thing. And if you're here, because you're now not multiplying this by 0 and add it to the thing from predictor 1, you get this thing. And then you get activations whenever there is, or high MR signals whenever there's a high value in either predictor 1 or predictor 2. Yeah? Is that clear? Because that's crucial, because this is about the interpretation of the beta weights. Of course, these beta weights are not defined or given by us to the participant or something, but they will be estimated. But then the important thing is, although we haven't really talked about estimation yet, I thought there was another thing with estimation. No. If we would estimate these parameters now based on the data, they of course would be quite similar to the theoretical values. So when we look at beta estimates, then if we have some observed data like this, then the beta estimates will of course come out roughly like this. If we have observed data like this, then the beta estimates will come out roughly like this. Yeah, so we will talk about estimation a lot once we've done the model formulation. For now, it's important that you see that voxel specificity with respect to certain conditions maps onto the relative values of beta parameters in the beta parameter vector. Yeah? So if you have a voxel that is equally responsive to two conditions, then the beta parameters associated with that voxel will roughly be the same. Of course, if the voxel wouldn't respond at all to anything, then they would also be similar but equal to 0. If a voxel is more responsive to one condition than the other, then the beta weight for the condition that the voxel is more responsive to will be larger than for the other condition. And then the final thing that is done in terms of now using brain imaging is to ask about the difference between the beta parameters. So essentially, if we assume now we have an estimate here, whatever that means in detail, but we have an estimate here that for predictor 1 says 1 and for predictor 2 says 0, then what brain imaging is always interested in is the difference. So the difference we can of course form by multiplying this vector by what is called a contrast vector that has a 1 for one condition and a -1 for the other condition, because if we of the beta parameters, if we now multiply this, we get of course 1 minus 0, we get 0. If we do this for beta b, where we have something around 1 1, and we multiply this again with this contrast wave vector, oops, that goes wrong, 1 minus 0 is 1. If we multiply 1 minus 1 with this vector, then we get of course 1 minus 1, and then we get 0. Yeah. So we look at the difference. So these are these contrasts that you come across. We will talk about contrasts in more detail when we talk about t-statistics. These are the beta parameters. In typical, of course, usually it's not only that we look at the beta parameters, but also at the estimated variance parameter. We will also get to that. But kind of the sign and the size of the resulting t-statistic is actually a function of the beta parameters and their relative value. And then if we, for example, have a region where the response is strong to one condition but not to the other condition, then this would be visualized in this typical kind of blob overlay that you see in the brain, or that you see in brain imaging studies. So for the moment, although you don't really know what a t-value is yet, you should keep in mind that t-values represent the difference between beta parameters, and if one beta parameter is a lot higher than another beta parameter for a given voxel, this means that this voxel responds a lot more to the predictor or the stimulus that is encoded by this beta parameter, as compared to the other. And I think this was already what I wanted to say about the GLM at this point. So maybe let's summarize that here. So this is a voxel time series. X is a matrix of MR signal predictors. And they arise from stimulus onset convolution. With hemodynamic response functions, or with one hemodynamic response function. The beta parameters encode predictor or condition specificity of a voxel. And of course the epsilon is independent, IID, let's call it, IID Gaussian noise. Oh, that's actually a good point. Let's call it Gaussian noise, because we will later see when we actually talk about fMRI, the IID is not always the way to go, and actually things may be non-IID when we talk about covariance components. So although you for now only know IID, we will later deviate from this IID assumption and put in also error correlations. But this is kind of the GLM for fMRI. And the big thing that we need to discuss then next is this stimulus onset convolution. Questions about the application of the GLM to fMRI data at this point? Something that remains unclear.
Is this Gaussian noise part somewhat related to the probabilistic, uncertainty, subjective uncertainty in Bayesian statistics as well?
No. So what we are looking here at in the winter term is just frequentist statistics. And this Gaussian noise that is added, you can interpret in two ways. So one way to interpret is that actually in reality the MR signal arises purely from the x times beta, and then there are contributions that are not in the model that are all added together and together give this error at a given time point. Another way you can view that is that you model the data, you use a predictor and a prediction or a predicted data based on this, and everything that you don't predict you capture in this noise parameter. But this is not has nothing to do with Bayesian uncertainty about something, in the sense that people usually talk about Bayesian uncertainty. So it's because Bayesian uncertainty usually corresponds to uncertainty over parameters, and this is not a uncertainty over parameter. This is a either the unexplained variance that you model, or if you view it more from a physics perspective, these are contributions to the data that are not captured by a deterministic aspect. So I think the first explanation is a little bit more reasonable. So this is basically all data variance that you don't explain. And in this sense, you can call that, but don't confuse it with parameter uncertainty. It's something completely different. But of course, it's the unexplained variance that you account for. You say, okay, with my deterministic model, with my x beta, I can explain that and that much. Of course, I cannot explain the entire data pattern completely. So the rest, I assume, is Gaussian noise. Good. Any other questions? No? Good. Then I suggest we stop here and next time then go into actually forming these design matrices for fMRI, which is called first level design matrices, and is all about convolution of stimulus onset functions, where you have the time points of when you presented your stimuli, and you somehow get the hemodynamic response function in there. So that's then the next big topic. Yeah? Good, then we're done.